Okay, so we're looking at space, lesson 18. Make sure you've got lesson 18 open and ready to answer your questions. Feel free to pause, obviously, whenever you need to answer your own questions. So, most of Einstein's theories are based on abstract thought experiments, which we've already looked at. For instance, the idea of time dilation and relative simultaneity are both deduced based on thought experiments involving trains, light, and mirrors. Although the thought experiments do not lack logic, they deviate quite a lot from reality because trains or spacecraft cannot travel at relativistic velocities, except obviously this train. Get it? Because it's light. It's a light train. Anyway, even if a train does travel this fast, it is then impossible for an observer outside the train to observe anything and make any accurate measurements for the events happening in the train. In the time dilation thought experiment, it would be impossible in reality to see the single light beam travelling up from the light source and then reflecting back from the mirror. What we'd see is just the whole train light up. In the relative simultaneity thought experiment with the light-activated doors, in order to observe any noticeable effects, the train needs to be infinitely long, like this one. This cannot be achieved in reality at two levels. Firstly, it's simply impossible to construct such a train. And second, even if such a train is made, the observer will not be able to see the doors at both ends of the train. So what we have to note is that only the logic is valid in thought experiments. The experiments themselves cannot be reproduced in reality. Nevertheless, thought experiments are significant, as sometimes they are the only way we can deduce important scientific theories. Now, just like the ether model, Einstein's special theory of relativity also needed supporting experimental evidence. One such experiment uses atomic clocks. Now, these atomic clocks are extremely accurate and sensitive clocks that can measure time down to, and more precisely than, 1/1000th of a second. One supporting experiment involves two synchronized atomic clocks. One of these clocks is put in a jet plane, which is sent off to fly at very high speeds for a period of time, while the other one is left on the surface stationary. When the jet plane returns, the two atomic clocks are compared, and it's found that the two clocks are no longer synchronized. The time of the clock placed in the jet plane runs slower, as predicted by Einstein, hence time is dilated. Further evidence for special relativity is provided by muons, which are a type of subatomic particle. The type is a lepton. We'll look at that a lot more in quantita quarks, so don't get too upset if it's not making any sense, but don't replace it with a mumu. We're talking about a muon. Now, muons are formed in the upper atmosphere as a consequence of the interaction between the atmosphere and cosmic radiation. Muons are very unstable and are subjected to natural decay. They have a very short half-life, about 2 microseconds. Although they travel at very high velocity, with this short half-life, it's impossible for any muon to reach the Earth's surface, since the distance from the upper atmosphere to the Earth's surface is large, and all muons would have decayed before they could reach it. However, with the aid of advanced instruments, scientific laboratories have detected the presence of muons. Since muons are travelling at relativistic velocity, their time will be dilated as measured by a stationary scientific laboratory. That is, muons' extremely short half-life of 2 microseconds, as measured when they are at rest, will be lengthened significantly, long enough for them to reach the surface of the Earth. The fact that muons are detected at the surface of the Earth provides very strong evidence for the validity of special relativity. In 1909, it was noticed that beta particles, as you guys would know them, electrons, emitted by different radioactive substances possessed different charge to mass ratios. So basically they had different electrons weighing different amounts. The various particles were travelling at significant fractions of the speed of light. Furthermore, the greater the speed of the beta particle, the smaller was its charge to mass ratio. When the effect of mass dilation was accounted for, the beta particles were all found to have the same charge to mass ratio. Modern particle accelerators demonstrate mass dilation every time they are used. As they accelerate particles, such as electrons or protons, to relativistic speeds, ever greater forces are required as the particles' masses progressively increases. Now, the next thing we're going to talk about is what's called the twins paradox, and it's often brought up when we talk about relativity. Now, it's a problem that's posed to illustrate a limitation with special relativity. So what I want you to do is consider two identical twins who have just celebrated their 17th birthday. One of the twins is put on a spacecraft and takes a very long trip to a distant star at a speed close to the speed of light, while the other remains on Earth. The Earth twin sees his own state as stationary, while the space twin rockets off. Thus, he sees the time in the spacecraft ticking more slowly than time on Earth, observing time dilation. Hence, the Earth twin concludes that he will age whilst the space twin is travelling, and the space twin will age less and will be younger upon his return. However, from the space twin's perspective, he is at rest, while the Earth twin moves away at a relativistic speed. Thus, the space twin concludes the Earth twin's clock is running slower and will therefore expect the Earth twin to age less and be younger upon their reunion. However, they can't both be younger than each other, hence the paradox emerges. However, if you truly analyse the journey, you'll notice that it is not a paradox after all. The paradox is resolved when we take into account the limitation of special relativity. Special relativity is only valid for inertial frames of reference. The Earth twin, who is at rest, remains in the same inertial frame of reference throughout. Therefore, his conclusion is always valid. The space twin, however, is not in an inertial frame of reference, as the space twin has to accelerate to move away from the Earth, make turns, and decelerate to come back. Thus, during these periods of acceleration, the space twin occupies a non-inertial frame of reference. Consequently, the space twin's conclusion is false. Now we look at special relativity's implications for space travel. As we've discussed earlier, the increase in mass as the speed of a spacecraft approaches c means that it becomes more difficult to further accelerate the spacecraft once its velocity becomes relativistic. This factor limits the speed of the spacecraft, with the maximum speed being one that is slightly under the speed of light, even in an ideal situation, that situation being an extremely powerful engine. Unfortunately, compared to the vastness of the universe, this speed is extremely small. Consequently, space trips will take an extremely long time. For example, a trip to our closest star, Alpha Centauri, will take 4.3 years, even when travelling close to the speed of light. As we've seen in the time dilation section, time in the moving frame appears to run slower. Hence, if a spacecraft can travel at a relativistic velocity, then its pilot's time will run significantly slower. Therefore, they will age much less compared to people on Earth. This means the extremely lengthy space travel as observed by the people on Earth, say 4.3 years, will be reduced considerably according to the pilot's perspective. So it'll be about 0.61 years if their velocity was 0.99c or 99% the speed of light. This allows the pilots to make prolonged space travel within their lifetime. Obviously, if we were traveling at the speed of light, which we can't quite do yet. So when a spacecraft is moving through space, relative to the pilots on the spacecraft, the space in front of the spacecraft is moving towards them. This means that the distance of the journey will appear shorter to the pilots than that being measured by people on Earth. Consequently, it will take the pilots a shorter time to reach their destination. Now, before we conclude this topic on relativity, I want to make clear some distinctions with the different types of relativity that we've already looked at. Firstly, there is plain old relativity, which states that all steady motion is relative and cannot be detected without reference to an outside point. This we've covered in detail. We did it in the prelim as well, I think, and it should be pretty easy to understand. This is just straight up plain relativity. Einstein took this concept further with his theory of special relativity. In this theory, he proposed that the speed of light was constant and space and time become relative. Several years later, Einstein built on his special relativity theory to include gravity. This is referred to as the theory of general relativity. This concept is not covered in the syllabus, but seeing as though it's pretty straightforward, it's worth mentioning. In a nutshell, the theory states that any object with mass distorts space-time, like the yellow sphere. It's distorted that grid of white. Therefore, other objects like the blue sphere continue to move in straight lines, which is Newton's first law. It's going to continue in motion, but the object curves because space-time is warped. This gives the effect that we call gravity. So the larger the mass, the larger the distortion of space-time, and hence the larger felt gravity. This concept is easy to grasp, but it's the math that is ridiculously difficult to understand. And it's well known that many university professors will still have difficulty in following it. And it comes down to the fact that some of it is like as we've talked about before, where Einstein had to make up his own sort of style of maths to solve the problems. And in this case, I think there's a little bit of that, and it's also just very, very deep maths that's definitely well beyond the scope of the HSC syllabus. So, like I said, the syllabus only requires relativity and special relativity. I just don't want you to get confused later on with when you ever hear the term general relativity, and I don't want you to get those confused. So, what I suggest you do is read the content on special relativity from both textbooks to help you clarify any misunderstandings you may have on the theories, because I know that some of my explanations may not have been fantastic, or it may just help to get it from a different perspective. How someone else has explained it might suit better the way you think, especially when we're looking at such abstract concepts. I'll also be granting you access, probably through Google Drive, to another text called Keep It Simple Science, which you may have had access to in other subjects, like chemistry or junior science maybe. This is a good source for revision, but I really want you to be mindful that it has been simplified greatly. It doesn't go into any detail whatsoever, so don't use this as a primary source for revision. It's just often difficult concepts can be understood better if they've been simplified. But you'll also find that it contains a lot of questions that you may find helpful to assist in testing your understanding. Now, over the holidays, make sure you use your time wisely. This will be the biggest break you get during your HSC year. Make sure that you are completely up to date, not just with physics, with all your subjects, but particularly physics. And make sure your notes are good. Spend time on them, make them good, because the space topic will be the first topic you forget. And when we come to your trial, you go, oh man, I can't even remember that stuff we did in space. If you've got really good, thorough notes, this won't be a problem. I'd also consider redoing some of your projectile questions so you don't get too rusty on that. I think that is a real skill, doing those, and you need to practice it, so don't forget to keep practicing those. For the remainder of this lesson, there are a few essential revision questions. Complete these whilst paying, as usual, close attention to the verbs. Now, if I don't see you before the end of the term, have a fantastic holiday, get lots of study done, have your notes completed and ready for me to check on the first day back of term. There will be consequences if I don't see those on the first day back. Be good to your parents and also find plenty of downtime, because when school starts back, you have got to go into overdrive just like Daniel Bryan here.